You have noticed it. Across most farms and gardens, fertility is treated as something that leaves with the harvest. Each season, crops grow by drawing nitrogen, phosphorus, potassium, and trace minerals out of the soil. Those nutrients become part of leaves, fruits, and roots. And once the crop is removed, a portion of that fertility goes with it. Over time, repeated harvests reduce what remains in the topsoil unless something is added back. This is why modern growing systems are built around replacement. Compost is spread before planting. Manure is worked into beds. Mineral amendments are applied to correct deficiencies. In larger operations, synthetic fertilizers are delivered in measured doses to maintain predictable yields. The pattern is familiar: grow, remove, replenish, repeat. Without that cycle, soil productivity usually declines. Most staple crops have relatively shallow root systems, meaning they rely heavily on nutrients available within the upper layers of soil. Once those layers are depleted, external inputs become necessary to sustain growth in the following season. This has shaped how farms operate for generations. Not only what they grow, but how they prepare fields between harvests. Fertility in this model is something managed from the outside. So the assumption took hold quietly over time. If you want to keep growing, you have to keep adding. Entire industries developed around making sure you could. Yet in many gardens, another pattern has been forming. One that does not rely on spreading compost or delivering fertilizer from somewhere else. It begins with a perennial plant known as comfrey. Unlike most garden crops that need to be replanted each season, Bocking 14, a sterile cultivar of Symphytum times uplandicum, can remain in the same soil for decades once established. After the first growing season, the plant develops a deep crown that supports rapid regrowth from the same root system again and again. When the leaves are cut back, new growth begins almost immediately. In favorable conditions, this cut and regrow cycle can repeat every 4 to 6 weeks during the growing season. Gardeners often harvest multiple times per year from a single planting without any need to reseed or replace the plant. Because Bocking 14 produces little to no viable seed, it spreads primarily through root division rather than self-sowing, which makes its growth easier to manage in controlled spaces. Over time, what begins as a single transplant becomes a permanent fixture in the garden. This kind of persistence is unusual among plants used for soil fertility. Most green manures or cover crops are annuals, sown, grown, cut down, and then planted again the following year. Comfrey simply returns from the same root mass, continuing to produce dense leaf growth without re-establishment. So while most fertility systems depend on timing and repetition, this one changes the timeline entirely. Once planted, the cycle does not restart with the season. Beneath the leaves, comfrey is doing something most crops are not built to do. As the plant matures, it develops a thick taproot system that can extend several feet into the subsoil, often reaching depths well below the zone where annual vegetables draw most of their nutrients. While shallow-rooted crops rely on the upper layers of soil, comfrey continues growing downward, accessing mineral reserves that remain out of reach for many garden plants. This matters because nutrients do not disappear when topsoil is depleted. Many of them simply move deeper through leaching, settling into lower layers over time. Comfrey's root system allows it to tap into those deposits. As it grows, the plant absorbs elements such as potassium, calcium, and nitrogen compounds from deeper soil horizons and transports them upward into its leaves. These nutrients then become part of the plant's biomass, effectively concentrating materials that would otherwise remain unavailable near the surface. The process is slow and continuous. There is no digging, no tilling, no mechanical intervention. The plant simply extends its roots, draws what it can reach, and stores it above ground in the form of dense green growth. Over repeated harvest cycles, this movement creates a shift. Nutrients that settled beyond the reach of most crops begin returning to the topsoil, not through external inputs, but through plant growth itself. Once those nutrients are stored in the leaves, they can be returned to the soil without ever leaving the garden. How? Well, it's quite interesting. When comfrey foliage is cut and laid around crops, a method often called chop and drop, the leaves begin breaking down within days. Because they are soft and moisture-rich, they decompose far more quickly than woody materials or straw-based mulches, releasing potassium, nitrogen, and other minerals back into the topsoil as they collapse. This makes the nutrients available again in the same zone where most vegetables feed. Gardeners also use the leaves to produce liquid fertilizer. When submerged in water and allowed to steep, comfrey foliage breaks down into a concentrated plant feed, sometimes referred to as comfrey tea. The resulting liquid contains soluble nutrients that can be applied directly to soil around fruiting crops such as tomatoes, peppers, and squash. In compost systems, adding fresh comfrey leaves often accelerates decomposition by increasing nitrogen content within the pile, helping balance high-carbon materials like dry leaves or shredded stems. None of this requires transport, storage, or external processing. The fertility is produced on-site, harvested by hand, and returned to the same soil where it began. With each cut, comfrey produces more than just leaves. It produces volume. Under favorable growing conditions, established comfrey stands can generate large amounts of leafy biomass over the course of a season. Agricultural trials and field reports have estimated that well-managed plots may produce tens of tons of fresh foliage per acre annually, with some intensive systems reporting significantly higher yields depending on climate, soil quality, and cutting frequency. This matters because biomass is fertility in motion. Every leaf contains nutrients drawn upward from deeper soil layers. When that leaf is cut and returned to the surface, those elements re-enter the zone where shallow-rooted crops can reach them. Over multiple harvests, the process repeats, deep uptake followed by surface return. Unlike livestock-based fertility systems, this does not depend on feed inputs, bedding materials, or manure management. The plant itself generates the material that becomes mulch, compost activator, or liquid feed. And because comfrey regrows from the same root crown, this production can continue year after year from a single planting. Instead of importing fertility from elsewhere, the soil begins receiving it from within the system itself, through continuous plant growth. By the mid-20th century, comfrey was no longer just a garden experiment. In Britain, horticulturalist Lawrence D. Hills began studying the plant as a potential fertility system for both small farms and home gardens. Through work associated with what later became the Henry Doubleday Research Association, Hills focused on selecting comfrey varieties that could produce large amounts of leaf growth without spreading uncontrollably by seed. This led to the development of Bocking 14. Unlike common comfrey, Symphytum officinale, which can self-seed and spread widely, Bocking 14 is a sterile hybrid, Symphytum times uplandicum, propagated through root cuttings rather than viable seed. The cultivar was selected for high potassium content and vigorous regrowth, traits that made it particularly suited for use around fruiting crops such as tomatoes and soft fruits. Hills promoted the plant not as a supplement, but as a foundation. In his trials and publications, comfrey was described as a way to reduce reliance on imported manures and fertilizers by generating fertility directly within the farm system. Cut leaves could be applied as mulch, added to compost, or steeped into liquid feed, all from a planting that remained productive for many years. For a time, the idea gained traction among gardeners and smallholders. The possibility that soil fertility could be maintained through perennial plant growth began moving beyond theory and into practice. Around the same time these trials were taking place, agriculture was moving in another direction. After the Second World War, synthetic fertilizers became more widely available through industrial-scale production. Nitrogen could now be fixed through the Haber-Bosch process, phosphate mined and refined, and potassium extracted from potash deposits, packaged into standardized blends that could be applied with mechanical precision across large fields. Fertility was no longer something generated within the farm, it became something delivered to it. This shift allowed growers to decouple soil productivity from local biological cycles. Instead of relying on crop rotations, livestock manure, or plant-based fertility systems, nutrients could be added in controlled quantities at specific growth stages. Yields became easier to predict. Application could be timed and measured. Inputs could be stored, transported, and sold. The system favored uniformity. Crops were bred to respond consistently to these inputs, maturing on schedule and performing within established supply chains. Fertility, once tied to living processes within the soil, entered a market built around repeat purchase. A perennial plant that generated its own nutrient-rich biomass did not move easily through that framework. It did not come in standardized bags. It did not need annual replacement, and it could not be distributed as a manufactured input. As fertilizers became products, fertility itself began to look less like a cycle and more like a commodity. So slowly comfrey's role began to shift in a different way. The plant had long been used in traditional herbal preparations, but scientific concern around certain compounds, known as pyrrolizidine alkaloids, started drawing attention during the late 20th century. These naturally occurring chemicals, found in varying amounts across comfrey species, were linked in some studies to liver toxicity when consumed internally in significant quantities. Health authorities in several countries responded by advising against the internal use of comfrey products. Over time, that caution began extending beyond medicinal contexts. Garden literature and agricultural recommendations increasingly emphasized restraint, even though the plant's use as mulch or compost material involves no ingestion. In public discussion, distinctions between internal consumption and external horticultural use were not always made clearly. Perception changed. A plant once promoted for soil fertility started appearing less frequently in formal growing guides. While it was never prohibited for use in gardens, the emphasis on potential risk reduced its visibility within mainstream horticulture. What had been presented as a resource began to look uncertain, and with time the system moved on. As fertilizer use became routine, the idea of generating soil fertility through plants began to fade from everyday practice. Annual inputs offered convenience. Nutrients could be applied in measured amounts, timed to crop growth stages, and delivered without the need to grow additional biomass within the system. For many growers, especially in larger operations, this reduced the time and land required to manage compost piles, green manures, or perennial fertility crops. Over time, the replacement model became normal. Fertility was purchased before planting, applied during growth, and adjusted as needed throughout the season. Soil amendments arrived pre-mixed and labeled. Recommendations were based on lab tests and standardized nutrient targets. The process fit neatly into planting schedules built around efficiency. Closed-loop systems required a different approach. Maintaining fertility through plants like comfrey meant dedicating space, harvesting leaves regularly, and integrating organic material back into the soil. It was slower to scale and less predictable across uniform fields. As input-based agriculture expanded, practices built around perennial nutrient cycling became less common in formal training and extension materials. Knowledge did not disappear entirely. In many gardens, comfrey remained in use as mulch or compost activator. But for new growers entering agriculture through input-driven models, its role as a fertility crop was rarely introduced. The plant stayed in the soil. The practice did not. But interestingly, in recent years, interest in soil health has started to shift attention back toward biological fertility systems. As growers face rising input costs, degraded soils, and more variable weather patterns, practices that maintain nutrients within the growing system have drawn renewed study. Regenerative agriculture, permaculture, and agroecological research often emphasize reducing external inputs by strengthening nutrient cycles already present in the soil. Perennial plants play a role in that conversation. Unlike annual cover crops that must be replanted each season, long-lived species can remain in place, producing biomass year after year from the same root system. When that biomass is returned to the soil surface, it contributes organic matter while releasing nutrients in forms accessible to nearby crops. Comfrey fits within this framework. Once established, Bocking 14 can provide repeated harvests of nutrient-rich leaves for many years, supporting compost systems or acting as a mulch around fruiting plants. The approach does not replace all forms of fertilization in every context, but it offers a method of maintaining fertility that depends less on transport, packaging, or seasonal purchase. The model is simple: grow the plant, cut the leaves, return them to the soil, and allow the system to continue from there. And that's it. So as conditions become less predictable, which matters more, efficiency today or resilience that lasts for decades? Share your thoughts in the comments section below, leave a like, subscribe, and turn on the notification bell for more amazing videos like this one.